Hey everybody, let's keep going with our electrophilic addition. Now this is the first reaction with a curved arrow mechanism for us in this chapter. But what's really great is that it's something that we have technically already learned before. We're just adding to the idea of some of the alkene reactions that we learned way back in chapter 8 and 9. When a double bond reacts, it reacts as a nucleophile. And so recall the Markovnikov addition of HBr to a carbon-carbon double bond to an alkene. The nucleophile will pick up a proton in a proton transfer. Now, when looking at this alkene, we have two positions. Hydrogen will go on the less substituted position, carbon number 1, so that the carbocation will go on the more substituted position, the more stable position, right? That was the Markovnikov idea, that we went through the most stable carbocation. Then, second step, nuke attack. Br minus will come back and make a new sigma bond with the carbon of the carbocation. So looking at carbons 1 and 2, H was added to carbon 1, Br was added to carbon 2. Now, two products are actually obtained when you use a conjugated diene. So I'm going to count out all 4 of these carbons, and what we're going to be able to investigate in this section is looking at 1,2 addition, where hydrogen and bromine get added to carbons 1 and 2, versus the 1,4 addition, where hydrogen gets added to carbon 1 and bromine gets added to carbon 4. What we'll notice is that the second double bond can actually interact with us in this reaction. And it's because of your absolute favorite concept, resonance. Now, when we're looking at this reaction, the first thing that happens is protonation, just like before. We will be dealing mostly with symmetrical alkenes, symmetrical dienes, so it doesn't matter which pi bond we react. What is important is the idea of Markovnikov. If you have an asymmetrical diene, the pi bond that will react is the one that will create the most stable carbocation, right? So when you're looking at what pi bond is going to react, be very careful. That proton transfer, step number 1, will always yield to make the most stable carbocation, all right? In our case, for the diene, it will always be the allylic carbocation, the one that can actually undergo resonance, all right? So this allylic carbocation is formed. I'm going to number these guys again, just so that we can see. Carbon number 1 gained the hydrogen, just like before. Carbon number 2 gets the carbocation. Now, one of two things can happen here. We can either go ahead and attack in step number 2, do the nuke attack, and add to carbon 2 for the halogen. So this would be a 1,2 addition product. Or, I'm going to erase that arrow real quick. And I'll make it red just so that we can see something different. Or resonance. And I'll highlight this blue. To where carbon number 2 and 3 now has the pi bond, and carbon 4, still an allylic carbocation, gains the positive charge. And bromine can add to the 4th position in another nuke attack. All right, so because there's resonance involved, there are 2 possibilities, and I'm going to label them blue or purple. All right, purple being the 1,2 addition, blue being the 1,4 addition. So whenever we are doing this reaction, the nuke can either attack the second position, carbon number 2 there, right, and do the 1,2 addition, or resonance can occur and the bromine or the nucleophile can attack the new carbocation. The addition of bromine to that conjugated diene will result in these two products, all right? So we have these two constitutional isomer products. Same idea with bromine diatomic. If you remember this reaction where we added Br2 to make a dihalide, we still see the same style addition. Now, we're not going to go through this mechanism, but it's interesting to note that a lot of our alkene reactions from last semester will result in the same type of 1,2 or 1,4 addition because of the new conjugated system. The ratio of 1,2 versus 1,4 addition, we're back to HBr here, all right? So back to the mechanism that we just went over. The ratio of 1,2 versus 1,4 is highly dependent on temperature, all right? So we can control the amount of product that we get based off of temperature. At 0 degrees, we primarily get the 1,2 addition. We'll talk about why. At 40 degrees, we will, for this specific example, 1,3-butadiene, at 40 degrees, we typically get the 1,4 addition. So we have thermodynamic control is what we call it, thermodynamic and kinetic control. We are able to preference one constitutional isomer over the other based solely on thermal control, temperature. So we're going to look at the energy diagram in order to understand why. All right, so that first step, step number 1 is the same. Hydrogen gets added and we make our allylic carbocation. Now, when we think about 1,2 addition, kinetically, we are doing that reaction faster for a couple of different reasons. And we'll talk about them in a second, but it's mainly due to proximity. Right? When we think about how quick the proton transfer occurred and Br minus is very close by, it's very fast for that Br minus to just go ahead and go right back and add to that carbocation. And so notice here, lower activation energy, meaning it's faster. And again, if you remember our discussion of kinetic, what is kinetic versus thermodynamic? Anything to do with reactant to intermediate is a kinetic factor, right? Kinetics, talking about how fast or how slow some reaction is. Now, on the other hand, the 1,4 addition way down here, look at this, releases the most amount of energy. It's the most stable at the end of the day. Why is it the most stable? Well, looking at the alkene, di-substituted versus mono-substituted. Di-substituted alkenes are more stable than mono-substituted alkene. So we're looking at that idea of mono, di, tri, tetra alkene stability. This is what we would call thermodynamics, because it is dealing with reactant to product, right? Nothing about how slow it is or how fast it is. It's solely looking at the end point, what is happening. So looking at these two options, the thermodynamically favored product will be the one that is more stable at the end of the day, and it will always be favored at high temperatures. Kinetically favored means whichever reactant going quickly to the product is always the 1,2. Now here's the key. 1,4 is not always the thermodynamic product. And so we're going to talk about why. And I have an example for us to just be able to identify that. The 1,2 is always kinetically favored. So the 1,2 addition is always the kinetic product, always going to be favored at low temperatures. The 1,4 typically is favored at high temperatures, but it's not always favored because it's not always the most stable. It's not always called the thermodynamically favored product. The thermodynamically favored product is the one that is more stable, right? So the more substituted the alkene, the thermodynamic control will occur. Now, and that will be favored at higher temperatures, all right? For this example, the more substituted alkene just happened to be the 1,4 adduct, the 1,4 product. So to wrap that up, if your 1,4 product is the most stable alkene, then it's the thermodynamic controlled product. If it's not the most stable, if the 1,2 is the most stable by chance, then the 1,2 is technically kinetic and thermodynamically controlled. So do not link thermodynamic with the 1,4 adduct as we have the kinetic control with the 1,2. Kinetic control is always 1,2, and we'll see that in just a second why. 1,4 in this example is the thermodynamically controlled product because it is the most stable, most substituted alkene. Why we get to link the kinetic controlled product with the 1,2 addition product is because it forms faster due to proximity. All right, so even at lower temperatures, the reaction is under kinetic control. The reaction product that forms faster is going to be the major product, and that is the 1,2, right? 1, 2 for the proton transfer. And there we go. Yes, resonance can still occur, but it's less likely that the resonance energy is going to be able to be met at low temperatures, right? Lower temperatures, less energy. And with that less energy, the molecule is just going to try to form the fastest that it possibly can. Here's another example of a symmetrical alkene, and I want to go through this one to truly understand that 1,2 versus 1,4 and the thermodynamic versus the kinetic style products, okay? I don't have a temperature here, right? This is just going to be draw both products, okay? So pi bond breaks. We are looking at 1, 2, 3, 4. Even though carbon number 1 here is tertiary and carbon number 2 is secondary, carbon number 2 is allylic. So again, we are forming the most stable carbocation, which is carbon number 2, okay? Carbon number 1 is tertiary, but remember an allylic carbocation is more stable than a plain old tertiary. I'm going to go ahead and draw my 1,2 product. So here's 1,2 addition. I will call this the kinetic product. If we had low temperatures at 0 degrees Celsius, this would be major, okay? Now, in order to understand the thermodynamic product, I'm going to redraw my carbocation. Just bring it over from right there and change colors. And I'm going to do the resonance and then draw out the 1,4. And then we have to compare these two and say which product is the most stable. Okay, so there's the resonance. Here comes my nuke attack. This is my 1,4 addition, right? Now, looking at these two products, I know the 1,2 will always be favored at low temperatures, but a tri-substituted alkene versus a di-substituted alkene. The tri-substituted from the 1,2 addition is the most stable. So not only is this the 1,2 product and it's the kinetically controlled product, this is also the thermodynamic product. At 40 degrees, which is what we're calling warm, higher temperatures, right? Room temperature is like 25. So this is pretty hot. This will also be the major product. So no matter what, at any temperature, this product, the 1,2 product, will be major. The 1,4 will always be minor in this case. So what we have to make sure that we understand is that kinetic is always 1,2 addition. Thermodynamic is always the most stable product. It can either be 1,4 or 1,2 addition. You have to draw both products to figure it out, all right? Now, where is this in real life? Polymerization reactions undergo a couple of different ways. We can do radical polymerizations, which was discussed back last semester in chapter 10. You can also do cation polymerizations, and that typically happens with these types of 1,4 addition conjugated dienes. And so you can see isoprene used in a polymerization to make natural rubber. Chloroprene can actually be used to make neoprene, which is a synthetic rubber. And so we won't go through these reactions, but it is a 1,4 style addition where we are linking the 1,4 of these monomers in to make the polymer. Very, very interesting.